Hey guys, hope everybody's doing okay. Welcome to yet again another virtual lab on a snow day, and this one is on enthalpy of solutions. This lab is related to how hand warmers and instant cold packs are created, and the kind of thought process that goes behind what goes in those and what companies are looking for when they make these things. So it's a pretty neat lab, and there's some good applications to it as well. So what I want to do with you is go over the pre-lab real quick, and then you guys will watch the virtual lab in Edpuzzle, and then you'll be able to do the calculations and analysis and go from there. So I'm going to walk you through the introduction here real quick, and then you'll have a lot of time to work on it. So the introduction, as you scroll through it and as you look at it, is just a little bit of background on hand warmers and instant cold packs, and it goes over some of the information we've talked about so far, where we look at heat of solution and Hess's law basically here, where you could look at the enthalpy of reaction of, reaction 1, reaction 2, reaction 3, and if you put them together, you can get the enthalpy of your whole process. All right, so that's all this is here. As we scroll through it, Q equals mc delta T is an equation we're going to obviously be using in the lab today to figure out exactly how much heat is released or gained for these dissolving processes that we're going to look at. Important for today is the mass in Q equals mc delta T. That's going to be the mass of our entire solution. So it's the solute plus the solvent. So that's really important. C is the specific heat of the solution. We're going to assume that it is obviously mostly water. That'll be 4.184. And then the delta T is, of course, T final minus T initial. And it has that here for you. All right. So a couple pre-lab questions. Number one, a lot of this is actually a review from Unit 2. It says when chromium chloride, CrCl2, it's actually chromium 2 chloride, is dissolved in water, the temperature of the water decreases. Is the heat of solution, okay, exo or endothermic? And explain how you know. So let's take a look at how we figure this out here. My drawing is going to have to do here. So here is our beaker, or our styrofoam cup, our coffee cup calorimeter we'd be using in this lab. And here's your water that's in there. All right, and here's your thermometer, of course. And then we're going to add some solute to that. Okay? And all of these are going to be very soluble substances. All right? So we want to look at what's the heat of solution. So that's really that dissolving process. So the temperature of the water, that's important. The temperature of the water decreases. So we add this solute in here. Okay, it dissolves, right? And the temperature of the water goes down. That means you have to think, where's the energy going? The energy is going from the water into this dissolving process that's occurring right there. Okay? So since the temperature of the water went down and the energy went into that dissolving process, the heat of solution is endothermic here. Okay? That temperature, specifically here of the water, is going to tell us where that energy is going. Is it going into that dissolving process, or is it coming from that dissolving process and heating up the water? Okay, so that's how you want to think of these things. So if you look at the second one, letter B, which is stronger, the attractive forces between the water molecules and the chromium and chloride ions, or the combined ionic strength of CrCl2 and the intermolecular forces between the water molecules. So it's to reference Unit 2 information on intermolecular forces to help. All right. So you want to think this through here. It's an endothermic process. So let's think of our process when dissolving occurs. This might look familiar to you from Unit 2. What we need to do in order for the chromium 2 chloride to dissolve, we need to break the intermolecular forces of water. Okay, that's the hydrogen bonding holding water molecules together. That needs to be broken. We also need to break the ionic attractive forces in CrCl2. Okay? Both of these are endothermic processes, right? It takes energy to break the intermolecular forces, that hydrogen bonding in water. It takes energy to break the ionic attractive coulombic forces between the Cr+2 and the Cl-1 ions. Okay, that is old news. We talked about that before. That is occurring here. What else is happening? Well, we're going to form ion dipole attractive forces between the Cr+2 and water, okay, specifically the negative end, the oxygen part, and the Cl- and water, specifically the hydrogen part. Okay, so we're forming these ion dipole attractive forces where, right, we would have like our Cr+2 ion, and then we would have a bunch of water molecules around it like this. Okay, so that is what we have going on here. So that's our negative end of water, the oxygen, right? And the opposite would be true for the chloride. This, remember, when attractive forces are created or formed, that is very exothermic. So all you want to do is ask yourself, if the overall process, this whole process here, is a dissolving process, we're breaking the IMFs in water, breaking the ionic attractive forces in CrCl2, then we're creating those ion dipole attractive forces between the water and those ions. That whole process for this example is endothermic. So that's telling you which of these two sides here is going to be the stronger attractive forces. Since the overall process is endothermic, then these attractive forces must be stronger. This is taking a lot of energy to be put in and break those, right? Less energy is given off when the new attractive forces are created. So here we are. So the attractive forces between water molecules and chromium and chloride ions, that's over here on the right. That is not stronger. Okay, it's still exothermic, but not very exothermic compared to, not as much energy as released as compared to how much has to go in to do this. So the ionic bond strength of CrCl2, that's here, and the intermolecular forces between water molecules, that's here. Okay, this is the process that occurs every time dissolving happens. So if it's an exothermic process, then this side is stronger. If it's an endothermic process, that side is stronger. Really easy. A review of Unit 2. Pre-lab question number 2 here is just finding the Q of solution. So here's where we want to use our Q equals mc delta T, and it says to use equation 1, which is the mc delta T formula. So pay attention to your units and all that, and make sure you solve that correctly. It shouldn't be too hard for you to do. All right. And it says calculate the heat released. That's important here. It's really, really important. Calculate the heat released as the solid dissolves. A release of heat is an exothermic process. So your sign on Q should be a particular value there. All right, when we have an exothermic process. We know that already. Question number 3. The solid in question 2 was aluminum sulfate. I give you the formula. Calculate the molar heat of solution, delta H solution, for aluminum sulfate. And look at the units here. We did this before in the enthalpy of combustion lab, something like it. The units here on heat of solution are kilojoules per mole. So we want to first determine the heat released per gram of the solid, and then we want to convert that into moles, of course. All right, so if you go back up here, all right, we had 25 grams of solid. All right, we want to figure out our kilojoules per mole of solid. So all you want is your units of kilojoules divided by moles, and that's about it. So figure out your kilojoules, which you kind of did up here in number 2. Figure out your moles of aluminum sulfate. I'll go down here, divide them, round to proper sig figs, and you're going to get your answer of heat of solution. All right, that's how you work out and do the pre-lab. So the lab itself, you'll see a video on how it's done. I would definitely recommend, if you're on Zoom doing this, or like a Google Meet or FaceTime or whatever, get some people from your class or even another class, and you can work through these calculations together. I definitely recommend doing that, even though we're at home doing the virtual lab here. So what you would have done in school, you can see on the video when you watch it, you're going to take a bunch of solids, combine them with water, they're going to dissolve, so you see our dissociation equation occurring here, and we're going to determine what the temperature is. So we're going to have a thermometer in our coffee cup calorimeters, and we're going to determine what that temperature change is, and therefore solve for Q. All right, so here's the process that you're going to go through. Here are the directions. The one that's going to happen, the one that's going to be shown to you in the lab is the sodium hydroxide. So we'll go through and you'll fill in this, you'll calculate this, and then you'll determine these, and you'll calculate this. All right, so you're going to look at how much water you're using, the mass of your compound, total mass of solution. Remember I talked about that in the pre-lab. You're going to look at the mass of the whole solution, because we're looking at heat of solutions here. Initial and final temperature of water to find your delta T. That will be, you'll follow along in the lab, get that data. The rest of this, I will provide you sample data, so you can do your calculations. Okay, lab calculations underneath. Determine the Q of solution, equation 2 from above. For each of the 5 solutions, you want to find Q solution right here. Remember, the mass is the mass of the entire solution, not just the water. It's important to convert your final answer to kilojoules and show all your work. So it's basically MC delta T here, and please keep in mind what your charge, what your sign is on that temperature change. It's T final minus T initial. That is going to tell us if this is an endo or exothermic process, so we should care about that here. So the exothermic reactions are going to have a negative Q value, and the endothermic are going to have a positive Q value. You'll do that for all of them. It won't take you long at all. Number 2, determine the molar heat of solution for the 5 solutions. We did it in the pre-lab. That's why I went over this and talked about it with you up here. All right, so we want to find it in kilojoules per mole. So what you'll need to do is obviously figure out, you'll have your kilojoules from here in part 1, and you're going to need to find out what your moles is. So you're going to need to use your mass of just the compound. It tells you right here. Mass of the solid, right? Convert that into moles and figure out your kilojoules per mole here. You're going to use that later on in the lab, so it's important to make sure we do these the right way. So make sure you look here. You should not use the mass of your solution. You should just use the mass of the solid compound. That's important because when we're converting from mass into moles, we need a molar mass. Well, if you have sodium hydroxide and the water here for your mass, how do you combine both of those molar masses? It's not really that simple. It doesn't work that way. So we're going to find out just the heat of solution in kilojoules per mole of the solids. All right, that's important. Really easy once you do that. A couple more mass calculations, what you got to do. Here's your post-lab analysis, and here's that real-life application to this lab. Using the results from your lab and information below, and the material safety data sheets, which I'll tell you how to find in a second, you're going to figure out which of the solids would be best used in a cost-effective hand warmer that's non-toxic and minimally harmful to the environment. So if you ever use an instant hand warmer, obviously you want them to be relatively cheap if you're the company that's producing these. So you don't want to spend a lot of money making it because you don't want to, you're not going to sell it for a lot of money, obviously. So you want it to be relatively cheap. And here I give you the cost in dollars per kilogram of the solids. All right, these are all the ones that you used in the lab. You want it to be non-toxic. All right, so that's key here because people are going to be holding them. It's a hand warmer, so you want to make sure they're non-toxic. So what you want to do is look up these different substances. I tell you to right here to find the material safety data sheet, which is what I get when I order all these chemicals. I get copies of all this stuff. Go to Google, type in sodium hydroxide, MSDS. You'll find 4 trillion of them that show up. They're all basically the same. Scroll through it, and there's a section of the material safety data sheet that goes over the hazards. All right, so briefly look over it, and if it's extremely toxic or harmful, you probably don't want to use it in a hand warmer. Okay, that you're going to be holding. And then, of course, when people are done with these, you throw them away. So you want them to be minimally harmful to the environment. So again, you'll find some information in your material safety data sheet about that. You don't want to pick something that's going to be cold. So you don't want to pick something that is you're not going to increase the temperature, of course. So you want to make sure you could eliminate those right off the bat, the ones that are endothermic. And you want to figure out what one releases a decent amount of heat, it's non-toxic, minimally harmful, and then tell me which one it is down here. So all you have to do is make sure you include your information from the lab, okay, your kilojoule per mole information, material safety data sheet, toxicity information, and cost information that's down here. So you need to compare all three things. All right, so I'll definitely be looking for that when you're doing the lab in your response. Finally, the last question is number 2. It is multiple parts, but it is not that bad. Most of this is related to Q equals MC delta T and figuring out what is your energy release and then unit manipulation like we've done so far in some of the other labs and calculations that we have done. All right, so I try to give you a couple hints along the way. So it's a little bit of a confusing setup here, but you want to look at the warm water for letter A. So you'll be doing Q equals MC delta T for that. Letter B is simple. Talked about that before. And here you're just looking at units. So you want to find energy per gram. All right, so you're looking at kilojoules per gram. Get your units there that you need. I give you a hint here that you're not using MC delta T. All right, I want kilojoules per mole. I'll give you the unit there that you need. You can find percent error. We've done that a million times. And down here, you're explaining what happens to the heat energy that's absorbed during the time when the temperature doesn't change. So this is when you're going through a phase change right here. We talked about that as we went through the some of the notes earlier on in the unit. All right, guys. I'll be available here and there for help. Check the roadmap for when that is, or if I see you in school, we can talk about any issues you have as you go through this. But hopefully this gives you a good rundown of what you got to do. If you were following along as I went through this, then you should be in good shape. The virtual lab is in Edpuzzle. It's only a 2-minute video, and you should be able to knock out the rest. All right? Thanks, guys.